Okay, so let's talk about instantaneous rate of change. So in the previous video we talked about average rate of change, and we talked about how to find that. You need 2 points. You connect those 2 points with a linear line, and then you find the slope of that linear line, and that gives you the average rate of change. Now the difference between average rate of change and instantaneous rate of change is, for instantaneous rate of change, you want to know what's happening at every individual point along a graph. So you want to know at one particular point, how is the function changing at that one spot. And if you remember from our driving analogy that we use for average rate of change, if you do the average rate of change, you don't get information about one particular point. You just get an average value over the entire section. So like in our previous example we used for the last video, we talked about driving from Kansas City to Denver at 2 different speeds. And we said that the average rate of change value gave us one speed for the entire trip. So it never told us what we were driving at each instance. It just told us on average what we drove over the entire trip. Instantaneous rate of change is what will tell you what you're driving at every single point along the trip. Now, finding instantaneous rate of change is something that we're going to need calculus to do, and we're going to need something called a derivative to do that, and we will talk about that in future videos. But for right now, let's just talk about instantaneous rate of change as a function of average rate of change. So for this example, let's figure out what the instantaneous rate of change at x equals 0 is for this particular graph, which again is y equals x cubed. And I have the x equals 0 spot denoted with the pink/purple dot right at the origin. So we want to figure out how is this function changing at that one particular point. Now you remember from average rate of change that you need 2 points to make a line, and then the average rate of change is the slope of that line. Well, if we're wanting to figure out what the change at one point is, we can't make a line because you need 2 points to make a line. So the way we're going to do this right now is we're going to estimate what the average rate of change, or what the instantaneous rate of change is at that one point by using the average rate of change of surrounding points. And the way we're going to do that is, let's start with the black points. So we have a point close to x equals -2 and x equals 2, and we're going to find the average rate of change between those 2 points. So there's our line. So again, if we find the slope of that line, that gives us the average rate of change between those 2 black endpoints. Now you know that for y equals x cubed, you know that at x equals 0, the function is 0. The function is flat. It's not changing at that point. You know it's flat at x equals 0. So for this example, we know that the instantaneous rate of change should be 0 at x equals 0. Obviously the slope of this line is not 0. So this is a bad estimate. So since we know that's a bad estimate, we're going to make the interval smaller. So now let's use the green points, and let's do the exact same thing. So now we have a linear line connecting those 2 green points, and sorry, it's a little off on the left side, but you get the idea. We're connecting the green points with the linear line, and let's find the average rate of change. Well, you can see the slope of that line is not as steep. It's flattened out some, so the slope is smaller. But we're still not anywhere close to 0. So our window is still too big. So now let's take a smaller interval, and let's use the blue dots now. And let's do the same thing. There we go, fix that. So now we have that blue line. And if we find the slope of that blue line, again, the slope of that is less steep than the green one. So we're getting closer to 0. But we're still pretty far off. If you're using the blue line to estimate the value, or estimate the rate of change, not the value, but estimate the rate of change at that pink point, you're still going to get an answer that's pretty different than what's actually happening. So let's make our window even smaller, and let's use the brown points. So now there's our line connecting the 2 brown points. And you can see the slope of that line is pretty small now. So by shrinking our endpoints and making them closer and closer and closer to x equals 0, we're getting a slope of a line that gets smaller and smaller and smaller, which means our average rate of change is getting smaller and smaller and smaller, which means we're getting closer and closer and closer to what the instantaneous rate of change at that purple point is. And if we wanted to be even more accurate, we would continue to make our intervals smaller and smaller and smaller. Now, this is something that we're going to learn how to do with calculus, and we're going to learn this through limits and through derivatives. So this will get much easier as we move throughout calculus. But for the time being, this is how you would estimate what the instantaneous rate of change is. You would just continue to shrink your interval until you got closer and closer and closer to the point you're interested in. And once you got to a close enough error, once you get close enough to the actual value, then you can stop and just estimate that that is the instantaneous rate of change at that point.